So, I mean, we've seen a lot today, a lot of really interesting personal history, hopefully some sense for the breadth of the power of the tool to study the normal brain and to make a contribution today to our patients and an even broader contribution tomorrow. But as I kind of gave some allusion to at the beginning, there are implications for the kind of work that we do, beyond the simple technology and our understanding of individual neurocircuits. Because in fact, more than most scientific discoveries, fMRI and the ability to kind of peer into the human brain and mind is something that captures the public's imagination and thus has broad implications. Probably not, a month goes by that I'm not driving and hear some new fMRI study being reported, on NPR or appearing, on the pages of The Onion as another opportunity to be lampooned. But the result of this is that people pay attention, and they've paid attention in a number of different fields. And our final session and our final two speakers are really going to capture some of these broader societal implications. Our first speaker is Josh Buckholtz, who I'm delighted was able to come here today. Josh, of course, is in the psychology department at Harvard University, has done some beautiful work on the concept of self-control, and perhaps, through his interest in self-control, has developed an interest in the consequences of the absence of self-control, and that's, our legal system. So in addition to his work at Harvard, he's also a network scholar for the MacArthur Foundation's research network on law and neuroscience, and I think we'll have a chance to share with us some of his thoughts on these important and broader societal interfaces of his basic work. So with that, please take it away.
Thank you so much to Bruce and Gary for the invitation. It's a real thrill to be here today. Because there are so many trainees and students in the audience, I wanted to impart you with two absolutely critical but also completely contradictory lessons. And the first lesson comes from listening to the stories this morning about what it was like to be on the cutting edge of this amazing field that has exploded and become so important. And I was listening to these stories, and they're actually always my favorite things about talks, because you can always read someone's paper, but you don't know what it was like to be there until you hear them talk about it. And I was also, though, filled with an enormous amount of guilt and shame, because I was reminded of the fact that in the late 1990s, so my dad is a neuroscientist, and we would have lunch every Saturday, and he would tell me all of these things that were happening in neuroscience, and he would talk about this really cool, weird stuff that was going on at MGH, and all of these studies of attention and memory, and I thought to myself, Jesus, I cannot think of anything more boring than that. My dad had just lost me at that point. And it wasn't until, because I was a sketchy kid and made lots of bad choices, and so I didn't care about memory or attention or visual columns. I cared about why people made the kind of terrible choices that I made all the time and were so costly to me. And it wasn't until a 2000 cerebral cortex issue on the orbital frontal cortex, which was the first set of imaging papers that I ever read, that I realized how dumb I was at that time. And so the first lesson is, kids, you don't know what you're talking about. You think things are dumb, they're not dumb. You don't know what you're talking about. Okay, so the second lesson pertains to how I got here, because it's weird that I'm here. It's weird that I'm here talking about this, because I'm a neuroscientist. I would prefer, truthfully, to be in my lab doing neuroscience. I have no qualifications for talking about this stuff at all. Stephen Morris, he knows this stuff. What am I doing here? And the reason why I'm here is because when I first went to Vanderbilt, I went to Vanderbilt because I wanted to learn PET receptor imaging with David Zoll of the dopamine system, because I was interested in reward circuitry and self-control and all of that good stuff. But, you know, in neuroscience programs, you do rotations, and my first rotation was with this guy, René Marois, and he had this collaboration with Owen Jones in the law school, and they pitched this study about the neuroscience of third-party punishment, of legal punishment. And I was like, fine, what do I know? And that study turned out to be, I got a, first authored neuron paper my first year of grad school. So at that point I was like, yeah, neurolaw, this is a thing we're doing. This is a real thing. And as I began to talk to more and more people in the law and have conversations, I began to be increasingly unsettled. And I began to have some really grave doubts about this endeavor that we seem to be undertaking. And this was crystallized in an interaction that I had with another parent at a daycare drop-off who happened to be a public defender in Nashville. And I said, hey, we're doing stuff, the intersection of neuroscience and law, what would be useful for you? And he said, oh, this is really great. This is exactly what my clients need. If you could devise an imaging test of the capacity to form requisite intent, that would be super helpful. And so, I didn't know what that was, and so I said, yeah, totally. I agree with you on that. And I went home and I looked up what that was, and it was like this flash and I was like, that's ridiculous. That's a terrible idea. That could never happen. And the fact that no one is saying that could never happen is a real problem. And so, but I was a grad student. What the hell do I know? So I kept my mouth shut, expecting that my more learned colleagues would start to articulate some of these really grave issues that I seemed to be grappling with all the time that didn't seem to bother anybody else. So I waited, and no one said anything, and no one said anything. And then, I was being interviewed for something else, and someone asked me a question, and I just said what I thought. And so the interview became about that, which was the ridiculousness of bringing the types of neuroimaging studies that we were doing in the lab, which were phenomenal neuroscience, into the courts. And so, somebody asked me to write a paper about it because they were really excited about their forensic genetic program. And so they wanted some, press for it. And I agreed because, grad students will write anything, for publications. And, you should. If you don't, you should write anything for publications. And I wrote this piece on the abuse of neuroscience, on the abuse of imaging and genetic information in forensic psychiatry in the law. And, he was horrified, and it became a big row. But in the end, I was able to convince him of the rightness of the argument. And so this second lesson is, yeah, you're dumb. You don't really know much of anything. But the people that you think do really don't either. And so you should probably just go ahead and say something if you think that you've identified some real issue, some real problem. It doesn't matter your status. Talk about it. Write something. Get it online. And so with those two mutually contradictory lessons in mind, I want to celebrate the fact that we're here to not memorialize, but to celebrate a sort of a miraculous thing, like on a dreidel, how it says, it's a miracle happened here, Some really special thing happened 25 years ago here. And this idea that we could capitalize on the magnetic resonance properties of gray matter to image the active thinking human brain is phenomenal. And cognitive neuroscience since then has developed at a pace that could scarcely be imagined given the humble origins that were described this morning. And the ensuing 2.5 decades have witnessed an explosion of ingenious techniques and sophisticated tools. And many of us here have experienced, to our delight and to our horror, each new advance in brain imaging is greeted with a chorus of febrile speculation about its potential applications to other arenas of human endeavor. Now, discussions about the promise of neuroscience for society are often tinged with this particular mixture of anxious hope and desperate fear. And nowhere is this more evident than discussions about the use of neuroscience in the courtroom. There has been a ton of excitement in both popular media and in scholarly publications about the impact that cognitive neuroscience is going to have any day now on legal cases. And this discussion is rife with speculation, but it all centers around the idea that brain imaging holds the promise of detecting liars, of objectively determining criminal responsibility, of quantifying pain and suffering, and of predicting violent behavior. And all of this suggests that the law is an important and useful test case for considering how brain imaging might be used once it escapes from the lab into society at large. So this circle right here represents what the law might want neuroscience to do, by which I mean things that maybe the law doesn't think that it does as well as it could, and that maybe with the addition of neuroscientific techniques and tools, it could do better. And here we have what people claim neuroscience can do. And this could encompass everything from overwrought op-ed pieces to speculative law review articles to incautious statements that we ourselves as investigators make about the potential impact of our work. And this is what neuroscience can actually do, right? The rather more narrow set of inferences that can actually be made from real brain imaging data, given the limits of our techniques, pragmatic constraints that govern how we design experiments, and the nature of our statistical methods. And right here, that teeny tiny little intersection right in the middle, that's the sweet spot. Public understanding of what neuroscience can really do to make the legal system more efficient and more just. But this is tiny, this little area right here. I mean, we can, as our tools get better, maybe we can make it a little bigger, but it's still small relative to the size of these other circles that contain the claims that are made for neuroscience. But the problem is, how exactly do we define that intersection space, that sweet spot? As it turns out, no one really knows. There's been not really any systematic evaluation of this overlap, no consensus framework for aligning legal goals and social expectations with the reality, the cold, hard, brutal reality of neuroscience methods. And so one initial stab at this is to demarcate clear domains of engagement between neuroscience and law. In other words, to flesh out families of related use cases. And I'll now talk about 3 such domains so that we can get a sense of what brain imaging looks like when it flees headlong into the wilds of society at large. The first domain we can think of as dealing with mental states, using neuroscience to lift the veil, to know the unknowable, to see the unseeable, to truly understand the content of another person's mind. The uses of neuroscience, typically here brain imaging, in this domain are somewhat varied. They range from wanting to identify levels of intent in a criminal defendant to demonstrating bias, perhaps racial bias, in a witness or juror, quantifying suffering in civil cases, and of course, the specter that haunts this entire discussion, unfortunately, the ability to detect lies, which we'll get there. And here's some particularly lurid examples of battles that have been fought and are being fought in this domain, right? So you have fMRI lie detection. You have using imaging to provide evidence of a criminal defendant's past mental state. Lie detection again, broken promises, that got a lot of press for some reason. My favorite, functional MRI detection of deception after committing a mock sabotage crime. This is a very specific use case for brain imaging there. The domain of prediction is next, which deals with the use of biological measurements to predict someone's behavior at some time in the future. And the issue actually of prediction comes up a lot in law. We tend to think about the role of law as retrospective, but there's an important prospective component of the law, a prospective duty that the law has as well. So we're talking about predicting violence risk and also maybe treatment response for parole hearings, for civil commitment, things like that. The final domain is capacity. And when I talk about capacity in this context, I'm really talking about the capacity for self-control. And at the intersection of law and neuroscience, issues around capacity tend to cohere around three poles: determining maturity, quantifying impairment, and validating the presence or absence of some disease state. There is this folk psychological assumption that is at work in a lot of the thinking about capacity and its relationship or as an area of intersection between law and neuroscience. This folk psychological assumption is that there exists some standard capacity for self-control, a basic ability that mostly everyone has for putting the brakes on their behavior according to prevailing social norms. And following that, there's a belief that some folks, a very small number of folks, by quirk of trauma or aberrant development or some neural defect, that these folks lack this basic capacity. But the intuition is that it's either or, it's all or none. You either have it or you don't, and imaging metrics have been supposed by some to be a potentially useful index of the presence or absence of this capacity. So neuroscientific evidence in this domain is often aimed at reducing responsibility, So neuroscientific evidence in this domain is typically aimed at using imaging or genetic data to reduce criminal responsibility through the use of biology as a mitigating factor. And so you have this Italian court case where you have a lighter sentence for a murder case than would have otherwise happened because they showed that this individual had a particular genetic variant. You have people talking about using imaging metrics in the courtroom, as was alluded to in some of the prior slides, to make inferences about the past mental states of criminal defendants. You have structural imaging in this famous Burns and Swerdlow case that seemed to be a necessary and sufficient cause for the sudden development of pedophilia in an individual who had not otherwise experienced those symptoms. Bless you. Which you would think would be mitigating, but 70 state judges in Maryland who were just yelling at me very recently seem to disagree with that, but good faith and all. To me, some of the most disturbing abuses of neuroscience occur in the domain of prediction, though. You have people who truthfully should know better talking about, one day we're going to be able to use brain scans to identify children who might become killers, right? Screening to identify kids early on who are going to become criminals at some point, and things like that. So this represents an area that has some potentially chilling implications if carried out to their logical or illogical conclusions. So we have some areas here where it seems like neuroscience could potentially be useful for making meat and potatoes courtroom decisions. And as you can see from the preceding slides, people are more than willing to say all kinds of things about what fMRI and genetics can do, from defense attorneys and prosecutors and well-paid expert witnesses and poorly paid associate professors alike. You don't have to look very far to find someone who's willing to make extraordinary claims about the coming neurolegal revolution. And this is why we have to be really thoughtful and proactive about identifying the general and specific criteria that a certain bit of brain imaging evidence would need to fulfill before we can be confident that it's useful for making valid inferences about something that the law cares about for a given individual. And it doesn't take a lot of careful thinking before we come up against several really important and potentially fatal problems. The first is that neither law or neuroscience knows what the hell the other is talking about. And I mean that actually quite literally. This isn't, though, a purely semantic problem. It's not an issue necessarily of competing jargons, but something more fundamental and more damning. To a cognitive neuroscientist like me, legal standards or constructs like volitional capacity or irresistible impulse or the capacity to form requisite intent it's gobbledygook, it's meaningless. It doesn't map onto any specific mental processes. These are things that are not instantiated in any 1 or 5 or a dozen specific identifiable brain circuits. Brains were not built to do things like have volitional capacity or avoid irresistible impulses in the way that the law thinks about it. These are not valid species of human mental function, is the point that I'm trying to make. But conversely, standard neuroscientific terms like action cancellation or response inhibition or delayed reward discounting, each of which represent, in fact, a valid and distinct species of cognition that can be measured by us with known precision and reliability, all that is completely Greek to people in the law. So when the law endeavors to use neuroscience tools to assess an individual's volitional capacity, it can't specify which, if any, of these processes are at issue. And the major point here is that, for neuroscience to have any real relevance to law, people in the fields that are related to law and neuroscientists need a lingua franca, a common language. Otherwise, they're going to keep talking past each other. So I'm going to show you now some examples of legal standards that deal with self-control. These are how the law conceptualizes and measures self-control. Right? So that's on the left. And on the right, we have some neuroscientific constructs that pertain to self-control. Right? We know things like weighting in a continuous performance test. We have some idea of what that means. We know how to measure it. We know how distinct it is from other related cognitive capacities. Interference suppression with a Stroop task. Action cancellation with a stop signal task. The inhibition of a planned motor response. All of those things. And so I want to ask you, if you would be so kind, to show me which of the things on the left map to which of the things on the right. So it's not so easy, actually. There's no intuitive sense that would guide us, and there's no a priori consensus about how to link these legal constructs that pertain to self-control to scientific constructs that have to do with the measurement and assessment of self-control. And this is some examples here of two neuroscientific conceptualizations of self-control and their specific operationalization in experimental tasks. So we have two tasks here, both of which, if you put a gun to a standard off-the-street neuroscientist's head and said, what do these processes tap generally? They would say self-control. Both of these are measures of self-control. We have delayed discounting, in which people are asked to choose between a sooner but smaller and a larger but later reward. Right? Self-control, very important. And we also have a stop signal task that indexes the ability to integrate external stimuli with ongoing goal sets in order to flexibly modulate and guide motor responses, right? Obviously, that's self-control, right? So both of these things we talk about as self-control. They're obviously different, and neither of them map in any neat way onto the legal constructs that pertain to self-control on the left here. So I'm hoping that you see the problem with this, right? And let's assume that a man named John is charged with a violent crime, and he wants to argue that he has a mental defect that causes a substantial inability to conform his behavior to the requirements of law. One formulation of the test for insanity. Stephen, please correct me. Okay, great. That'll never happen again, by the way. Assume further that John performs poorly on tests that measure response inhibition, action cancellation, impulsive choice, but he has preserved functioning on tasks that measure attentional control, attentional selection, and feedback learning. This is a really nice neuropsychological workup. This is really excellent neuropsychology. But are the results of this test battery at all relevant to John's legal claim? Clearly, he has some significant impairments that we can measure in the lab in these knowable, identifiable, valid species of mental function, but do they have any relevance for the law? Maybe, maybe not. As of now, it's a difficult question to answer because the law's language is incommensurate with neuroscience's measurements. And so my only point here is that if legal policymakers want to take advantage of neuroscientific knowledge, then we all need to engage in some really hard thinking about whether, for example, it's difficulty in inhibiting one's responses, choosing long-range goals over short ones, or any of the other self-control domains that we can assess with some precision and reliability, if any of those should affect legal liability. As of now, we don't know. And so these things are proceeding in a very disturbingly reactive and ad hoc manner. And you have individual courts making these kinds of decisions without perhaps the appropriate gravity of wisdom on both sides of law and neuroscience that could help them figure these things out and tease apart this puzzle. I do want to say, too, that, it's totally reasonable for the law to say, no thanks, this is really spectacular neuroscience, but it's kind of irrelevant to what the law is trying to do. That's a perfectly acceptable outcome, totally acceptable response, but this is most fruitfully done systematically and a priori by demarcating specific legal standards for which there is consistent agreement that no viable scientific operationalization exists, or for which the law says, we don't either require or desire any scientific evidence to adjudicate this specific thing. The law is always free to decide that it doesn't need or want neuroscience to adjudicate legal standards, and there are many good reasons why it shouldn't. But if jurists do make these decisions based on their own moral intuitions or normative preferences or precedent, then they shouldn't be using scientific evidence as an empirical fig leaf to prop up the intuitions and the preferences that are really, in fact, driving those choices. I am just advocating more than anything for honesty and transparency at the intersection of these fields. So as grim as this picture is, I do think it illuminates a path forward. The lingua franca problem is one that I just talked about, but say that we're able to overcome this hurdle, right? So the lingua franca problem, what we need to do is we need to clarify legal standards. We need to get a clear articulation of what the law specifically might want from neuroscience. And then, together we need to come up with some sense of whether or not what they want is actually operationalizable in neuroscientific terms that could promote, a useful interaction there. But say that we've done that. Are we in the clear? Unfortunately not. And so we'll turn to the next problem, which is that it's possible to have legally meaningful inferences from brain imaging that are not scientifically valid. And this piece of the puzzle turns out to be quite the sticky wicket. So this problem, which David Fagman at UC Hastings has called the group-to-individual or G2I problem. And it has its roots in a very significant difference between the aims and goals of law and the methods of science. Science, as we know, is what we want to do is we want to understand universal phenomena, right? We typically aggregate data across groups of individuals to make generalizable inferences about the world. But law doesn't care about that, really. The law cares only about making a determination about the specific individual under consideration at that moment, a defendant, for example. Group or population level scientific data are only relevant to the law to the extent that the data bolsters or weakens the evidence provided about that individual in that individual case. Let me show you what I mean. Say that I take this lovely group of silhouettes and I put them in the scanner. In one condition, I ask them to lie about some set of facts. And in another, I ask them to tell the truth about some set of facts. And when I compare their brain activity when they're lying versus when they're telling the truth, I see this pattern of activity right here. I don't know if you can see that dot, but there's a little sort of asterisk in DLPFC, right? And this tells me that dorsolateral prefrontal cortex is more active when people are lying versus telling the truth. And as a scientist, if this comparison is statistically significant and I've use random effects analyses and yada, 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 I can make a formal general inference about lying, something like lying recruits a network involving frontoparietal control regions or something like that. So do we have a brain-based lie detector yet? Not so much. You might think that if you weren't smart like you are, that all we'd have to do with a criminal defendant is put them in the scanner, ask them to tell their side of the story, and if these brain areas become active, then that's our smoking gun right there. But the problem emerges when we look at each individual's brain activity level, right? So here we have arbitrary units, whatever else, subjects' activity levels in each condition. What we see is that activity in DLPFC is generally low in the truth condition, right? So we have the group average of 3.89. It's generally higher in the lying condition. So 20.3, it's going to be a statistically significant difference between those two conditions. But let's look at each participant's values here, right? If we have a defendant who is subject 4, and we're relying on this brain-based measure, you're going to erroneously conclude that they're telling the truth when in fact they're lying, right? And if the defendant is this individual 9 right here, then they might be convicted because you think they're lying when in fact they're telling the whole truth and nothing but the truth, right? So this is the essence of this group to individual problem. We as scientists make universal inferences about phenomena that are interesting to us that elide the fact that there's a ton of individual variability, and this only becomes important when we start interacting with a group of people who care about individuals, like people in the law. And so this is how much longer do I have? Don't do that. We'll be here all night, man. I got a lot to say. All right. In the interest of having someone who's more eloquent than I go sooner than later, I'm going to skip over some genetic stuff. But I want to talk now about some additional constraints that we have on any time that we're thinking about using brain imaging to measure what are incredibly complex behaviors. And the truth is an obvious one. Complex behaviors have complex causes, right? Complex behaviors are complex. This shouldn't be a surprise to anyone, and yet here we are. On the one hand, any interesting human behavior is going to be massively, multiply determined, right? And on the other, single causal factors rarely map with any specificity onto single circumscribed behaviors or syndromes. And this is just the phenomena of equifinality and multifinality that haunt all studies of complex human behaviors. And these are constraints that apply broadly and really should inform how we approach inferences about imaging in this context. I'll conclude by talking about a study that touches on several of these issues. This is a prediction study. I have not used any of Sue's work because I was focused on prediction studies that have lots of flaws. So many of the things that I'll be talking about, in fact, are done really well by the people in this room, which should surprise no one. That said, they're not always done as well as they could be. And so I'm going to talk about this study right here. And I'll say up front, this is a really neat study. They did something that's incredibly hard to do. They took a group of incarcerated criminal offenders and identified which ones were going to be released soon. And they scanned those individuals using a mobile MR scanner inside the prison. And then they tracked these people as they went off into the world, and eventually, one by one, were rearrested and reincarcerated because recidivism rates are really high. So it's very hard to do. Before they were paroled, each subject got a scan using a response inhibition task. And based on the beta weights for the focus of activation in anterior cingulate for each individual subject, they were grouped into high or low activity groups, right, on the basis of whether or not in that sample their ACC activity was on the higher end or the lower end. And what they found is that ACC group activity membership prospectively predicted rearrest latency. So the folks that had the weakest engagement of ACC during this response inhibition task, the folks there in red, those were the folks who were rearrested much more quickly, and the folks who had relatively higher activation during this response inhibition task in the ACC, those were the folks that managed to stay out of prison for at least 50 months. Now, you can see after 50 months it starts to get dark for them because, as I said, recidivism is always very high. So if we want to know if someone's going to commit crime, should we scan their ACC? Perhaps not. Considering equifinality, criminal behavior is so multifactorial that reducing risk to activation in a single brain imaging measure is just from first principles pure folly. And indeed, when you do appropriate confirmatory techniques for predictive modeling, like Russ Poldrack did once he got a hold of these data, the actual predictive power of imaging in this sample, while nominally statistically significant, appears to be so small as to make one question whether or not it's worth the cost at all. Considering multifinality, The anterior cingulate activation in the ACC is not going to be a specific marker for criminal behavior. It's most likely affecting a range of cognitive processes and behavioral predispositions that, in aggregate, are going to affect risk for committing crime, but are also associated with anxiety and schizophrenia and mood disorders. So predicting criminal behavior, in a narrow sense, that's true, but in a larger sense, what we're really likely tracking here are third variables that correlate with, but are not isometric with, risk for crime. And there are other inferential challenges here. Just a couple of quick ones. The authors are talking about using cingulate bold signal as a predictor of rearrest. We don't really have any sense of the retest reliability of this measure. We don't know what the population distribution of bold signal values is. We don't know the robustness of this measure to variability in task administration and data analytic techniques. And so we have this prediction that's based on a median split of bold signal, the units of which, I'll remind you, are arbitrary, meaning that any potential cut point or threshold used for prediction is necessarily going to be sample dependent, right? If I give a well-validated clinical instrument that assesses psychopathy, say the PCLR, to a subject at institution X, then their score should be equally meaningful when they're transferred to institution Y. Yet it's entirely conceivable that if you transferred all of the members of the low ACC group, putatively the low rearrest risk people, to another institution with a different distribution of ACC bold signal values, they could, after a median split on ACC values at that institution, become the high ACC activity group. So there is a disturbing sample dependency here that arises from the fact that we're ignorant as to the real population distribution of the values that are being used in these predictive assays. So this paper illustrates another important constraint, I'll say, for considering the utility of brain imaging for addressing social issues, right? The law cares about behavior, full stop. And so if what we're interested in is predicting behavior, why would we think that an imaging measure is a better prognosticatory tool than behavior itself? There is this sort of folk assumption that neuroscientific measures of cognition provide higher fidelity insight into our mental states and our intrinsic capacities relative to behavioral and self-report measures. And it's this assumption, actually, that drives much of the incautious enthusiasm around neuroprediction in the law. But notwithstanding the exciting work of Sue and John, evidence of incremental validity for neuroscientific data is actually quite sparse. And given the expense and the potential prejudicial nature of imaging measures, a rigorous evaluation of the incremental validity of neuroscientific data over and above mere behavior is what's required. And as regards the study that I just spoke about, that study by Aharoni and colleagues did find that including ACC activity in their model predicted reoffense risk better than behavior on the response inhibition task alone, right? So there's some incremental value there. But performance on response inhibition tasks isn't known to be a really major predictor of criminal rearrest. So claims about the incremental predictive power of bold signal over behavior has to be based on behavioral tasks that are already known to predict a target behavior with some, that has some useful value for predicting some target behavior. Otherwise, you're going to be stacking the deck. Better than behavior means nothing if the behavior that you're entering into your model has never been shown to predict your target behavior, which I imagine is the case for the specific task in that paper. So the point here is that a truly compelling demonstration of increased incremental predictive power for bold requires taking the best known behavioral or self-report or clinical predictor that we have and the best known actuarial predictor in the case of rearrest and entering these in the same model with individual bold signal values. So I've painted a somewhat grim picture here of the challenges that are involved in thinking about how brain imaging could really shed some light rather than just heat on thorny social problems. And many of these issues, I'll say up front, they're addressable. We are all very smart people. But ignoring these issues when we apply brain imaging to social problems is only going to ever serve to magnify those problems. Circling back to the law, the use of neuroscientific evidence to make legal determinations about minds and brains has to always be constrained by the limits of scientific inference. Good law cannot follow from bad or badly used neuroscience. And this same principle holds true regardless of the specific domain of human activity we're talking about, be it law or medicine or, God help us, neuromarketing. Thank you.